Hello, everyone. Welcome to Power Corner. I'm your host, Aalyia Shaukat, the editor-in-chief of Power Electronics News. Today, we're speaking with Dr. Noah Sturcken, co-founder and CEO of Ferric. Welcome, Noah. How are you doing today?
Doing great. Yeah, thanks so much for having me, Aalyia.
Well, thank you. Thank you for joining me. So we can just go ahead and jump right in. Maybe you could start off by covering a little bit of your academic background and research. I know you specifically focused on integrated voltage regulators or IVRs, and maybe you could start off with the story of how Ferric began.
Yeah, happy to do that. My family has been working on semiconductors and computing for multiple generations now. My grandfather worked at Bell Labs. My father worked and developed processors for NASA and other aerospace applications. So I don't know if it was innate or just that it was like part of my environment that,
It's very cool.
um,
Yeah.
developed, an appreciation for engineering. Let's see. Then, by the time I got to school, it was clear like that this is what I'm interested in doing.
Mm.
And so I worked, got my electrical engineering degree at Cornell, focused largely on processors, circuit design, and then spent some time at AMD where I worked on custom digital design for high performance processors.
Mm.
That experience really led me to recognize that power is an area that is kind of underappreciated, underaddressed for these products, for these high performance processors, and
Yeah.
that power integrity can have a really significant impact on the attainable performance and performance per watt. And
Mm.
so, as I'm like pushing to make an impact um, to push the capabilities of these processors forward, it's clear like providing a better power supply is the best way to do that. That this
Yeah.
is a under appreciated problem for the systems.
Thank you. And as you were saying, you've said that power supply noise is impacts circuit timing more than any design decision that you've made when designing high performance logic. I imagine that was at your time at AMD. How did observations like that, lead you specifically to magnetic materials as the main constraint rather than say, controller architecture or process node?
Yeah, so I guess by the time I had finished my undergrad and some time at AMD, I realized like there's an opportunity to do something disruptive, revolutionary in power delivery for these products. I joined a research group at Columbia University, so
Mm.
up the street from where I am now.
Mm.
Worked with Professor Ken Shepard,
Mm.
and based on Ken's perspective, his experience and connections in industry, we really kind of gained momentum on this idea of integrating power converters directly with microprocessors. And in order to do that, you need a short-term energy storage device.
Mm.
Inductors are really the preference for the, the most common power converter topologies. And so kind of one thing leads to the next, and you realize
Yeah.
we want to integrate these power converters to do that and actually do this in a practical way that could be used in industry. We need dense, high frequency power inductors. We need novel materials in order to realize that. And
Mm.
so
Yeah.
developing those materials became a key focus of my PhD.
Very cool. And from what I understand, there's kind of three distinct inductor approaches in commercial IVRs on the market. There's Ferric's ferromagnetic thin film, back end of line integrated inductors. There's the magnetic core inductors that are embedded at the package level, and also air core inductors integrated, I believe, at the package level or into the module. What do you think is the differentiating factor for Ferric's thin film inductors?
So our inductors are using ferromagnetic composite alloys that we've developed specifically for this application. And that means that we're able to build components that have very dense and low loss energy storage.
Yeah.
So this magnetic material can operate at a high frequency, and it can store a lot of energy because it has both a high permeability, but also a high saturation magnetization.
Okay.
So this becomes, a really useful medium for us to miniaturize these power converters by miniaturizing the inductors, switching frequencies to higher and higher levels, and in doing so, miniaturizing the total power converter system.
If Ferric's FE, I believe it's Fe1766, that includes several key advancements, and we talked about that, the back end of line integrated thin film ferromagnetics in a multi-phase interleaved buck operating at greater than 50 megahertz, which allows for a control bandwidth of 10 megahertz from what I've read. And what does that bandwidth figure mean for engineers? What's possible at 10 megahertz that might not be possible with conventional VRM bandwidths?
So just as a baseline, it
Mhm.
means that you can achieve better power integrity for your processor with less area, less capacitors, and thus achieve better supply voltage margins for your product.
Yeah.
Then, beyond that, with that higher bandwidth, there's an opportunity to implement more aggressive power management. So not only can you do a better job at keeping your power supply flat and well regulated when you want to, but you can also move that power supply around a lot faster than you could with slower converters. And so if you want to jump between power states in order to save energy, this becomes, I guess, a lot more advantageous once you have the IVR, because you can make that transition faster and you have less decoupling capacitance that needs to accept and release charge as you're making those transitions. So that sort of dynamic, sorry, Lee, just that
Please.
sort of dynamic voltage scaling, this has the potential to reduce power consumption for processors by another 30 to even 50%, depending on the workload, in addition to the power savings that are provided by the better power integrity and reduced supply voltage margins.
And that's incredibly important as we're working with AI workloads, with I suppose, those tighter constraints and transients, as you were.
Yeah, well, and just, order of magnitude larger total power consumption. So really pushing density and, exacerbating the impact of transients and poor regulation.
So maybe we could talk about Marvell's. They have there's several companies that are participating in being pre-validated in Marvell's package integrated voltage regulator ecosystem, so PIVR. And what do you believe is Ferric's biggest advantage here? Is there a scenario where a customer can deploy more than one solution simultaneously?
So I think, it's important for advancement in the industry that there be an ecosystem of IVR options.
Yeah.
For any one customer to adopt this technology and move forward, they're going to be a lot more comfortable doing that if they do have options, they have contingencies available. Now, of course, it's our goal to be the best, and to push the capabilities of our technologies so that we can confidently address our customers' requirements for current and future generation products. So we're going to continue pushing that. We're going to continue advancing our capability, and we'll likely be creating more distance between us and our closest competitors. But there are going to be options out there that can give our customers some alternatives that are available if necessary. Yeah.
Gotcha. Thank you. And speaking of that, it seems like IVR engagement now begins at the architectural phase of the SoC. So that means usually 9 to 12 months before tape out. What does that sort of depth of code design require from Ferric in terms of engineering resources, and has it changed how you think about the business?
So there are multiple, levels of integration that are available to our customers. They can take our IVR chiplets and put them directly on their motherboard using them in a rather conventional way. So that's the shallow end of the pool. It's available, and it's not unlike the design cycles using existing power supplies and PSIPs. Our applications team is experienced and very knowledgeable on these implementations, so that it's short work, and we're able to provide excellent support to those customers.
Gotcha.
On the other end of the spectrum, we have much higher levels of integration where our power converter is going into the package of our customer's processor. There are scenarios where we're doing new work, that this is pathfinding, and as a result, our applications team is a lot more engaged and responsible for designing the power delivery network, selecting capacitors, and overall making sure that we're providing excellent power integrity as is expected for the IVR, right? So we can kind of work along this path where we're maturing the technology at this kind of very advanced stage, and then there are a series of less aggressive integration options that are more mature and therefore lower risk for our customers. And they can select between these options, select all the above if they're aggressive.
Gotcha. Yeah, so I don't remember exactly the sort of different ways to deploy it, but I know that vertical power delivery is very fast becoming a thing, moving from lateral to vertical, and then you've got the backside of the motherboard, and you've got behind the PCB, then the backside of the motherboard, and then there's package integrated. Am I sort of correct?
That's correct. Yeah.
Okay.
So you can take a cross section of the processor on the motherboard. The VPD would go on the bottom side of the motherboard. The IVR is small enough that it can be integrated closer and closer to that processor. It can be embedded into the motherboard, attached to the bottom surface of the organic package substrate, or embedded into that substrate.
Okay.
And again, all of these different approaches have merit. We have customers who are using each of these, and in some cases, multiple of these different integration options for different projects with different goals. So I think really offering this flexibility is really important to enabling acceptance of this great new IVR capability.
Very exciting. Thank you. So I know that Ferric publishes a peak efficiency of 90% at 1.8 volts down to 0.75 volts, and that's for the Fe1766, as we were talking about earlier, and that's quite good. And it seems that maybe there's an inherent tension in IVR design between pushing switching frequency higher, which shrinks your inductor, enables a fast transient response, and its impact on losses. Given that you're also pushing current density higher than most competitors, and potentially operating within the geometric constraints of the back-end line integration, how do you think about that efficiency density trade-off?
So really, to enable integration into the package of the microprocessor, there's a minimum density that needs to be achieved. Otherwise, it just doesn't fit. And so that's often the first step for a customer to determine feasibility with our IVR, make sure that this is dense enough and can fit within the area available. So we pay attention to that. We make sure that we're exceeding this density threshold. Then from there, efficiency needs to be at least good enough so that you can thermally manage this system, right? So if your efficiency is 20%, you're wasting tons of power, creating a lot of waste heat, and just obviously isn't a viable solution. And so we've pushed aggressively not only to achieve this very high density in our products, but to have excellent conversion efficiency at that high density. So our 1766 product, for instance, with a steady state current density, so TDC of 4.5 amps per square millimeter, we're achieving just under 90% conversion efficiency. So that's not lower further down in the output current curve. It's really at the furthest right extent, that at max power consumption, we're at 90% efficiency, so that you can actually use the product.
Wow. Okay. And that was I had a follow-up question for that. Is peak efficiency at that single operating point the right metric, or should engineers evaluate performance across the full load curve?
Yeah, so certainly needs to be evaluated across the full load curve. Depending on the application, you might be spending the vast majority of the operating lifetime of the system at maximum maximum power. This is especially the case with AI applications. You're training a new model. The system is just crunching numbers at max power rather consistently, right? So again, you need to have high conversion efficiency at that max output power. Otherwise, it's just not as useful for the customer.
Yeah. Um, Maybe we could shift to the advantages of Ferric's foundry relationship with TSMC. I understand that TSMC is also experimenting with IVR technology, built on the 16 nanometer process. I think you told me about the they're licensing Ferric's ultra thin inductor. What are your thoughts on this? Maybe you could talk a little bit more about the relationship there.
Yeah, so again, this is a great development. We've worked very closely with TSMC and have worked very hard to mature that capability and get them into production with it. This is, yet another way to integrate power converters with high performance processors. There's multiple ways to address this problem. We've developed core technology that's really instrumental, whether it be on wafer or in package. And so, we're big supporters of TSMC. They're, critical partners of ours in our supply chain. And so we're, really excited about the advancement in the industry towards IVR in general. And again, have spent enough time developing solutions here that we have multiple options, whether it be through TSMC or through our standard products. Yeah, so in general, very excited about these developments and pushing these capabilities forward.
Thank you. What's the next significant technological milestone in Ferric's roadmap? Is it primarily materials or process integration improvement, or is it something at the package level?
It's a combination of these. And forgive me for being a little bit vague, that these are
It's okay. It's understandable.
important
Yeah.
plans to us, right? So
Yeah.
we've got this incredibly intelligent team that have now this excellent track record of developing new technologies specifically for this application. And with our latest and greatest inductors, our Gen 3 power inductors, we're achieving significantly better performance than is available elsewhere. Our team will be able to continue building on this capability. So basically making our inductors better and better, step by step, and in doing so, enabling our products to achieve better and better design points. As we go through that power converter optimization process, you can trade efficiency versus density versus input voltage, but all of those things can be improved as you have a better and better powertrain, a better inductor available. So we keep making that inductor better, we'll be able to continue making our products better. And our team is, in their element, driving this technology forward. So it's a really exciting time.
Yeah. Can I ask, when was the Gen 3 power inductor released?
So our first product that uses this Gen 3 inductor is our 1736.
Okay.
So with that product, we're achieving density of about 2.8 amps per square millimeter with 56 amps output TDC. We think launched this at APEC in 2025 and have been sampling it to customers and have this now in multiple AI computing systems as we speak.
Okay. And maybe we could talk about the roadmap a little bit. It seems that the overarching race is to achieve the most current dense solution and that maybe, 1 millimeter height. At what point does thermal management become the ceiling before density can go further? And do you agree that thermal management is even the primary constraint? Is it other things?
So, there's a trade again between density, efficiency, regulation, performance. And so certainly you could push density to an extreme. We could achieve 10 amps per square millimeter density right now, although our efficiency would be compromised and we would be generating more heat. And then the question is, how good is your thermal solution? as we're working with our customers, we're working within their constraints, within the thermal solution that they have available. And so it's important to reach this optimal design point where we have the right combination of density, efficiency, regulation performance, input voltage, all of these things, so that this is the right fit for our customer. And we described like multiple different integration scenarios. The thermal design for each of those can be different. And so thermal requirements and the impact of those constraints varies with different integration levels. For instance, embedding the part into the core is essentially the most challenging from a thermal perspective, but then worthwhile from an electrical perspective.
Gotcha. How does input voltage impact things in terms of, say, efficiency or thermally potentially?
So as the input voltage on buck converter in particular, as that's increased, it becomes harder and harder to achieve the density and efficiency that you want for IVR applications. Although, as you push that input voltage up, you enable better efficiency in the upstream power delivery system. So you can reduce conduction losses on your intermediate bus voltage. You can also reduce, the total amount of current and the BOM for that upstream power solution. But, the processor is still the most valuable component here. Making sure that you have the best power supply for the processor is the top priority. So again, meeting the density, efficiency, regulation requirements. This gives you a multiple on the value of that processor by making it more efficient and it is improving its peak performance. So again, prioritize the quality of power supply for the processor, and then as able, increase that input voltage so that the rest of the system can become cheaper and more efficient. And this is the strategy that we're executing at Ferric, that we have our products with 1.8 volt inputs that are handily meeting market requirements, and now we have an opportunity to expand.
Gotcha. Thank you so much for your time, Noah. This has been a really insightful discussion. I really appreciate it.
Yeah, I really appreciate the time, Aalyia. It's been very insightful here, and appreciate your time and attention.
Thank you. Thank you.